This problem is slightly more complicated only because there is the spring that has deflection already, which is 0.05 meters. As well, additionally, the cylinder that's on top of the spring, there's distance between that cylinder and the spring. So this adds some different initial conditions, but really the problem is very similar to the one that we just worked, because we're still looking for the max deflection and we're given information about the spring. So we have the two forces from the spring and the mass that we have to take into consideration. So we have the kinetic energy and the potential energy, and the change in that is 0. So we can plug in the information that we know, which T2 is at resting. So mgh we can consider, and with the mass is 6 kilograms times g, and that height traveled is the 0.1 meters that there's the distance between the cylinder and the top of the spring, as well as the deflection here. So that is going to be 0.1 plus delta. Then we'll have to take into consideration this whole distance here, because there's the integration that we're about to take, and it's already been moved some, so we'll take into consideration that whole distance by doing the integral from this 0.05 to delta plus 0.05. And what that looks like is 0.05 to 0.05 plus delta. And that way we've taken the whole spring into consideration, because you can't just take it from here to here, since that will change the deflection. And this is kx, and our k is 4,000. So 4,000 x dx. And that will be 0. And once you take that integration and multiply those values out, you get 2,000 delta squared plus 141 delta minus 5.89 equals 0. Solving for that is 0.0294 meters. So there's very, very small deflection of the spring once the cylinder lands on it. So you may have to convert that to millimeters in the solutions because it's fairly small. But we did the exact same thing that we did before. We just made sure that we knew what these conditions were, there and there.